Okay, this lesson is going to be about the operations with functions. By that I mean we're going to figure out different ways that we can combine functions. Now, you can do it with arithmetic. We can do it using addition, subtraction, multiplication, division. But we can also use it with something called a composition. So these are all the different things we're going to see about how we can combine different functions together. So first we'll look at the arithmetic method of combining functions. So generally the idea is you're using basic arithmetic to put two functions together, so addition, subtraction, multiplication, division. So first one, if you look at this one, it's addition, and this is more just looking at what the notation is. If I have two functions f and g, and when I look at these functions f and g, I want to combine them with addition. Well, one way to write it would be simply just f plus g of x. But really what that is f of x plus g of x. So you're just adding the two functions together. Now, how would you add them together? Well, it depends on the functions. If they're basic algebraic functions, you would use things you learned in algebra to help you combine those two functions with addition. If they're trigonometric functions, there's ways to do it, logarithms, exponentials, but these are all functions we haven't really dealt with. So mainly you're going to see this with your algebraic functions. And we'll have some examples in a second. You can combine your functions using subtraction. So this would be f minus g of x. But you can also basically write it f of x minus g of x. In that case, really all you're doing is subtracting the two functions. And it depends how you subtract depending on what kind of functions you have. But mainly right now we're looking just at the notation. Whether you write f plus g or f of x plus g of x, I mean, they mean the same thing. Multiplication, f times g of x or f of x times g of x. Now there's a very important part to the multiplication, and it's notation. Right here, this dot. If you look at that little dot, that's typically what you know to be the symbol for multiplication. Other symbols for multiplication would be f of x, times g of x, but we tend to not use the cross when we talk about multiplication, because in other fields of mathematics that cross means something else. We could just put the two functions next to one another, f of x times g of x, and that's the same too. But if you're going to use the dot, if you look at this dot right here, if you're going to use the dot for multiplication, make sure that dot is a solid dot. F of x times g of x. Because if it's not a solid dot, if it's an open dot, okay, that's going to mean something else that we're going to see in a few minutes. Then the other operation we can look at for arithmetic is division. So the division, we usually write as a fraction, but it doesn't have to be written as a fraction, but this would be f divided by g of x. F divided by g of x. Or just f of x divided by g of x. Now there's a trick to the division one that you just got to worry about, and it has to do with domains, and there's a little bit about that here. We say let f of and g be functions with overlapping domains. But really the idea is that the domain of each individual function may not be completely what the domain of the sum is, or what the domain of the difference is, and so on. And largely what you got to worry about is not so much these three operations here, but the last one. G of x on its own might have a domain, all real numbers, whatever it is, it'll have a specific domain. And 0 might be included in g of x's domain on its own. But if I put g of x in the denominator of a fraction, the denominator of any fraction cannot equal 0, okay? So I can't have this denominator be 0. So while g of x on its own might be able to equal 0, if I put g of x in the denominator of a fraction, because I'm using it to divide, that can't be equal to 0, so then that value would have to be omitted from g of x's domain in order for this division to be possible. Okay? Another way I could write the division is f of x divided by g of x. Right? It's another way you can write division. I could write it that way too. But all you're doing is dividing the two functions. Now, how do you do that? Well, it depends on the functions. So let's look at some examples. So here's two functions, very basic polynomial algebraic functions. F of x equals x squared plus 2x. G of x equals 2x plus 1. So find the following. F of x plus g of x. All right, so let's do this first one. F of x plus g of x. Well, if f of x is x squared plus 2x and g of x is 2x plus 1, then I have to add those two functions together. Now, how do I do it? Well, they're polynomials. So the only way you add polynomials together is by combining like terms. These are the only two like terms that I have, so I get x squared plus 4x plus 1. There's not a whole lot to it, but what I just did is I combined two functions into a new function. And that's a big part of this, is that when I add two functions together, I get another function. This is still a function. It follows the definition of a function. Each x gets matched to exactly one y. If I look at the graph would pass the vertical line test. So two functions combined together should get me another function. Now, that new function might have the same domain or a different domain as the individual functions, but it will be a new function. Let's try b. F of x minus g of x. Okay? Well, f of x is x squared plus 2x. G of x is 2x plus 1. And I have to subtract those two functions. Well, remember, this is polynomials, this is algebra. When you subtract a polynomial, one thing you got to remember to do is subtract all the individual pieces of that second polynomial. So how do I do the subtraction? Well, based off of what I'm subtracting, and I'm subtracting polynomials. So I have to subtract each of these terms. So what I end up with is x squared plus 2x minus 2x plus 1, or oops, see, now that's the mistake, minus 1. So 2x minus 2x, these two things are like terms, but they'll cancel. So then I end up with x squared minus 1. So this is what my sum is. Okay? Which is a new function again. So the difference of these two functions is a new function. Same ones, let's try different operations. Multiplication and division. Well, same thing. F of x times g of x. Okay? So that should be x squared plus 2x times 2x plus 1. So how do I multiply these together? Well, they're two polynomials. You multiply using the distributive property. X squared gets multiplied by the 2x, x squared gets multiplied by the 1, 2x times 2x, 2x times 1. So I end up with 2x cubed plus x squared plus 4x squared plus 2x. These are like 2x cubed plus 5x squared plus 2x. And this is my product of these two functions. Again, it's a new function. Okay. One thing to look at, if you go back, and I talked about domain, the domain of this original f of x is all real numbers. The domain of this g of x is all real numbers. The domain of the sum is all real numbers. The domain of the difference is all real numbers, because these are all just polynomials. And the domain of any polynomial is all real numbers. I can plug anything I want into here for x, I'll always get an answer. Again, the product is another polynomial. The domain is all real numbers. But something changes when it comes to the quotient, the division of these two things. So let's make some space. Alright, so we have to do f of x divided by g of x, which would be x squared plus 2x over 2x plus 1. This is what the division would be. Okay? So if I look at this and say, okay, well that's my division. I could leave it like that, as long as the fraction simplified and say, okay, that's my division. I could actually do the division. In that case, how do I divide polynomials? Well, I can do long division to do that. I'd say, okay, here's x squared plus 2x, here's 2x plus 1, and I divide. I take the first term inside, divide it by the first term outside. So x squared divided by 2x gives me 1/2 x. Multiply that, I get x squared plus 1/2 x. Subtract that line. So 2 minus 1/2 is going to give me 3/2 x. Okay. I can do this again. Take this divided by this, so I get 3/2 x divided by 2x gives me 3/4. So I add 3/4. Multiply some more. I'm going to get 3/2 x plus 3/4. Subtract, and I end up with minus 3/4. And I could do that, right? I could do that and say, okay, well this is the same thing as 1/2 x plus 3/4 plus negative 3/4 over 2x plus 1. But honestly, all that's probably overkill. Right now, we're just trying to get the basic idea of combining these two things together. So if we stop there, that would be fine for now. But this is some things you've learned in algebra about dividing polynomials. So I'm sure you probably need a refresher on that stuff. So we'll skip through the long division. We'll say, okay, this is the way we're going to write our answer. So I look at that and go, all right, well, what's the domain of that function? The domain of the original functions is all real numbers, but this one, the denominator can't be equal to 0. So when does 2x plus 1 equal 0? Well, if I solve for x, it's going to be when x equals 1/2, or minus 1/2, actually. So the domain for this whole function is x cannot equal this value. So the domain for f of x over g of x is x does not equal negative 1/2. Any other x will work. So it's almost all real numbers except for this one value. So to combine functions using arithmetic, it's essentially just using the things you learn in algebra for adding, subtracting, multiplying, dividing polynomials, or whatever type of functions you're trying to put together. Another way of combining functions together, though, that is different from anything you've seen before is what we call a composition. A composition does not use arithmetic to combine functions together. This composition function is a way of combining functions in a specific order, where you do one function first, then another function second, and so on. So the notation for a composition function is this notation right here. The way you read this is f of g of x. Okay? F of g of x. Now, with the two notations, the second one, I think, is a little bit easier to work with than the first one, and it kind of makes more sense. Whenever you see the parentheses in any mathematical expression, we typically use the word of to denote what that means. So if you look at the second one, f parenthesis g parenthesis x, this is f of g of x. It also makes it more sense in terms of what you're actually trying to accomplish. When you look at the second one here, what it looks like is that g of x is plugged into f, and that's exactly what you're going to be doing. But this notation with this open circle is another way of doing it. When you look at this open circle here, that's another way of sort of defining a composition or writing down the notation for a composition. And the key is that's very similar to the way we write multiplication, but it's not. So this composition is not multiplication, right? And I have it really big here. This composition function deals with order, not multiplication. So either way I write it down, f, this little open circle, g of x, or f of g of x, and this way it means do your functions in a specific order, and the order you're going to do is from the left back to the right. So in this case I'm going to do f of g of x, g comes first, f second. Okay, that's the order. And what I mean is I'm going to take g, evaluate g, the answer I get from g I'm then going to plug into f. Okay, now as far as domain goes, you got to make sure that your domain values for g go into f, and then so on. And then I will talk about that in a second. One way we draw functions is by drawing this mapping. This is kind of how we started the whole thing off. A function takes you from one place to another. Well, if I'm looking at this f of g of x function, I'm going to do g first. So this is the function I'm going to do. This is my domain for g. This is going to be my range for g. Okay? Then what I'm going to do is do f second. So then these range values, these answers I got from g, I'm then going to take those values and I'm going to plug those into f. And I'm going to get another set of values. In this case, this range is now what I'm using in my domain for f, or what I'm plugging into f. And then I'm going to get another set of values out of that. So this is sort of the range of f. Okay? But really what's happening is I'm doing two functions one after the other, sort of like skipping from one stone to the next. So g, then f. What f of g of x represents is going from here all the way to here. So this is f of g of x. And normally you read things left to right, but we're going to start on the right and work our way backwards. Okay? And g comes first, then f comes second. So I can do it twofold through a series of two functions. Okay? Or I can go all the way to here. Either way, I'm starting with the domain of g, and then I'm going here to the range of f. But it's not really purely the range of f, because it's only the range of f given these values in here. If I switch the order around, and I said g of f of x, well, it's just do f first. So f comes first, then g comes second. And if I'm going from 1 to 3, basically, this first set to the third set, that's what g of f of x would be. Okay? Probably we start to see it in an example, you'll be better off. So here's some examples. Here's two functions, same functions we were working with earlier, x squared plus 2x and 2x plus 1. So if I had to find a g of f of 3, I could also write this as g of f of 3 this way. And I think writing it this way is easier when you're actually trying to compute this composition. Because what it looks like is that f of 3 is plugged into g. So when I'm going to do this, what I'm going to do is first I'm going to find f of 3. And that's just evaluating a function, and you should be able to evaluate a function at this point. That was the first lesson that we did. So if I plug 3 into f, here's f. If I plug 3 into f, I have to do 3 squared plus 2 times 3. Okay, in that case I get 9 plus 6 equals 15. Alright. The second thing I'm going to do is then find g of f of 3. Well, we already found out that f of 3 is 15, so really what I have to do is find g of 15. And think about it, when you've been doing order of operations for as long as you've been doing math, and parentheses are involved, what do? You'd work with the innermost parentheses first and work your way out. And that's kind of what we're doing here. So then I have to find g of 15. Well, here's g, and I got to plug 15 into g. So if I do that, I go 2 times 15 plus 1. So that gives me 30 plus 1 is 31. So that means f of g of f of 3 equals 31. And what's really happening here is this. I'm doing f first, then I'm doing g second. And what's happening is I plug 3 into f, I get 15, I plug 15 into g, I get 31. So if I want to jump from 3 to 31, g of f of 3 will jump me from 3 to 31. Alright, let's look at another one. Let's do the same functions, but I'll flip the order around this time. Let's ignore these two examples for right now. Let's do f of g of 2, which I can also write as f of g of 2. Okay? So I look at this and go, alright, f of g of 2. First thing I'm going to do is work from the inside out. And again, you can write it either way, but I think this second way, it makes more sense in terms of trying to actually compute this value. So the first thing I'm going to do is find g of 2. Well, g of 2, look at what g is. Okay, 2x plus 1. So I have 2 times 2 plus 1. So that's going to give me 5. So then I have to find f of g of 2, which is really f of 5. If I look at what f is, I'm going to do 5 squared plus 2 times 5. So I get 25 plus 10, 35. So if I do g first, then f second, I'm going to go 2 to 5 to 35. Or 2 can go to 35 using f of g of 2. Okay? Alright. Now, you're not always going to have a specific number that you're going to plug in here. So, that's where these next two examples, B and C, are going to be. If you look at these next two examples, it's f of g of x and g of f of x. There's no number in those B and C ones. So, finish this up, erase, erase, erase. Alright, so if we look at B, f of g of x, okay, which is the same thing as this, f of g of x. The idea is we're combining two functions together and we're getting a new function. What that function is going to be found using this method, because we're not using a specific number, we're still just using the general variable x. So what are you going to do? You're going to do the same thing. First thing is, what's g of x? Well, g of x is 2x plus 1. So the second thing is to find f of g of x. Well, g of x is 2x plus 1. So what I have to do is find f of 2x plus 1. Well, I got to plug 2x plus 1 into my original function. Here's my original function. So I got to take this whole thing here and plug it in to this function for x. So I'm going to have 2x plus 1 squared plus 2 times 2x plus 1. Now if I square this one, I'm not going to just square the 2x and square the 1. It's 2x plus 1 times 2x plus 1. So I get 4x squared plus 4x plus 1 plus 4x plus 2. Combine my terms, I get 4x squared plus 8x plus 3. So when I drew this three pebble thing where we have one set goes in an x into an x, in this case it would be g first, f second, and then I said it can jump from here to here. Well, the function that takes me from here to here, there are two functions that take me here to here, but there's one function that takes me from here to here, and that one function is this function right here. This is the function f of g of x. Right? And that's the function that takes me from 1 to 3. Okay? Now normally if you flip that order around and instead of doing g first you do f first, you really shouldn't expect to get the same answer. There are certain times when you will get the same answer and that's going to mean something, but generally when you flip it around you shouldn't expect to get the same answer. So if we look at this here and do the other one, and we do g of f of x, well, g of f of x shouldn't give me the same thing as f of g of x. Alright, erase. Alright, so if we look at g of f of x, which we also can write as g of f of x, well, f of x is x squared plus 2x. And that's really what I have to plug into g. I'm plugging f into g. F first, do f first, then get f and plug it into g. So if I plug f into g, when I plug anything into g, I take and I multiply that by 2, and then I add 1. So what do I get? 2x squared plus 4x plus 1. This is not what we just got a second ago. This is saying, okay, let's do f first, then let's do g second, okay? And I could do those two functions one at a time, or I can also go and just skip from step 1 to step 3, and I do that by using this new function. This new function is g of f of x. The only other type of question that you might get when it comes to some of these compositions is sort of the opposite question. They give you the answer that you got after you did a composition, and you got to figure out which functions could give you this answer. Now, there are multiple answers actually for these types of problems. Sometimes there's only 2 answers, sometimes there's 10 different ways you can do it, but any way you do it is fine. Just, you got to get one of them. So if I'm trying to say, okay, find these two functions, f and g, so that when I do the composition this way, f of g of x, which basically means when I take g and I plug it into f, I get this function here, which is x plus 1 squared. And the way you kind of do this is, you got to think about this, is there's a function inside of another function. That's what a composition really is. A composition is a function inside of another function. So if I can look at this thing and say, is there a function inside of another function here? And usually the parentheses are the best way to do it. If you think about it, this function here, x plus 1, is inside of this function, which is the square. So if I looked at that and said, okay, let's let g of x be x plus 1, and let's let f of x be x squared. Well, if I took x plus 1 here and I plugged it into here for x, I would get x plus 1 squared. So this x plus 1 squared can be thought of as a composition of these two functions, g and f, where g is x plus 1 and f is x squared. Because if I did f of g of x, I'd have to do f of x plus 1, because that's what my g is. I then take x plus 1 and I plug it in for x, and I get x plus 1 squared. So usually these aren't too bad to do, but you're probably not used to thinking about x plus 1 squared as a function inside of a function. But now that we've talked about compositions, you should start thinking about it that way, as I have one function inside of another function. One more. So if we erase, give you one more. If you really, I mean, it's all kind of about the parentheses for most of these. If I said, alright, let's do a new problem. H of x equals 3 times 2x minus 3 to the third. Find f and g such that h of x equals f of g of x. Okay, so h of x equals f of g of x this way. Same thing. G is inside of f. Well, again, if you kind of look at this, 2x minus 3 is inside of this other function. Well, what's the other function? Well, if we let g of x equal 2x minus 3, then f of x has to basically be everything else, which is this 3 and then this third power. So 3x to the third would be my f of x, and if I took this and I plugged it in there for x, I would get the original function.